Okay, welcome to Note Set 21. We're now going to really drive home how useful the DFT is. We're going to take a look at the relationship between these three things and ultimately show that if we can compute the DFT, that we can see the DTFT to some degree, and we can control that degree, and that will allow us to see what the CTFT looks like. And that's the real big idea. So again, it's important to realize that this DFT it's our powerhouse numerical processing method for doing Fourier transform processing. It allows us to numerically do this. We can take in the signal, take its samples, do this DFT processing on it, and find out what frequencies are in the signal. And that's an exceptionally powerful thing that we can do. So here's the setup for how this might work in an actual processing scenario. So we've got a continuous time signal that comes in from a microphone or some sort of sensor. There may be some continuous time system that processes that before it gets to the A to D converter. But ultimately it gets there, maybe an anti-aliasing filter of some sort. The A to D converter creates samples, x of n, taken at the rate of fs. We assume that that rate has been chosen properly to make the aliasing error as negligible as necessary. Those samples get streamed into some sort of memory array. There's no real constraint as to what kind of memory it could be, although there may be other constraints that say it needs to be some sort of fast RAM or something, but somehow we need to get it stored inside our computer, and for our purposes we just say, well, they're stuck into some memory locations, and there they are. And so we've got n samples, so from 0 to n minus 1. And then once we have all the samples, we do DFT processing using the FFT algorithm. So the FFT algorithm computes n DFT values. Now we're going to modify this later when we talk about zero padding. So here we're not talking about doing any zero padding per se, but we'll talk about that later. So we use the FFT algorithm to compute the DFT values, and those get sent out into some memory array. In some applications, these two memory arrays are the same, and we just overwrite our original signal samples. Other scenarios, we would need two separate memory arrays, but that's not important to our discussion here. So we dump those into some memory somewhere, and it's these things that we're interested in looking at. We can plot those versus the appropriate frequency values, and the goal is, by plotting those things, to look at them and have the plotted DFT tell us something about the CTFT of this original signal. So our goal is to try to do all of this and minimize the errors and discrepancies between what we see in the DFT and what really is there in the CTFT. So we need to explore all this mathematically so we understand how it works. So the first thing, we already know pretty much the connection between the DTFT and the CTFT. So if we can connect these two things, then we will have a complete understanding of this. And we're going to do this by considering two different cases. We'll start off first talking about the finite duration case, where the actual signal under study is literally finite duration. So zeros all down here and zeros all down here. Now we only start with this case because it's an easy place to start, and it provides some basis for doing the other case, which, not surprisingly, is infinite duration. The idea is that not only is this a finite duration signal, but we capture only those points that are non-zero. So that's the part that makes it unlikely to actually happen in practice, because we generally don't know when a signal is going to start and stop. But let's just analyze this case and see what happens. The other case that we'll look at is infinite duration, and in reality that can never happen, right? Because how could a signal be infinitely long in both directions? But the idea is that the actual duration of the signal is longer than what we actually collect. So we might start collecting sometime after the signal has actually started, and we might stop collecting sometime before the signal actually starts, or before the signal actually stops. So you've got some signal like this. We don't necessarily know how long it's going on in either direction, but we may only grab stuff in this region. So for our purposes, this might as well continue infinitely in both directions. So we'll analyze this under the assumption of infinite duration, but we know that that's really a misnomer. The important thing is we don't have all of the meaningful signal data. We don't have this out here. We don't have this out here. And we need to know what effect does that have. What impact does it have as far as understanding what is actually in the signal? So these are the things that we're going to analyze. So we'll start with the finite duration case. So we're going to assume that we have all of the signal samples that are non-zero. So here's the theoretically complete DTFT, and we've collected all of the non-zero values. So everything that we have is in this, and we've not left out anything except for the zero valued terms. So we have everything exactly. Okay, so if we take these n samples, and instead of putting them into this theoretical equation of the DTFT, we compute the DFT, probably using the FFT algorithm, and we do this on a computer. For simulation and exploration purposes, we would do that in MATLAB. For actual implementation, we would do it in some sort of specialized processor, hardware, and software. But here's our DFT of that, and we just literally wrote down equation-wise what we have here. And let's compare this. If we compare this, what we see here is, if we look carefully at this argument, we see that what we're really doing, the kth DFT point, is really the DTFT evaluated at k times 2 pi over n. So what that's telling us is that the DFT values that we compute lie exactly on the finite duration signals DTFT. So the dotted red line is the actual DTFT of this thing computed like this, and the big red dots are the things that we compute here. So for the finite duration case, where we've captured all of the signal data and nothing but the signal data, we get exactly this idea. We see the DTFT perfectly, and that's really the best that we could hope for. So summarizing, for the finite duration case, we've got these signal samples give us x of omega. These signal samples give us the x of k, but the x of k are just perfect samples on the DTFT. Now, the number of samples that we have sets how closely spaced these DFT points are. Now, that seems to be some sort of limitation, but let's just show a little trick here. This is that zero padding trick that we've been alluding to. And this is not just limited to the finite duration case. We'll be talking about it, using it for the infinite duration case as well. So the zero padding trick says, so I've collected those n actual value samples, or all the non-zero value signal samples. And what we do is we tack on some additional zeros at the end to trick the DFT into thinking that there are really more samples than we have. But in this case, notice that what we're really doing is we're just extending this sum. We're just tacking on some zero terms. It's as if we're grabbing the values of x of n that have 0. So for the finite duration case, zero padding is like we're just grabbing some extra samples that really are 0. So it doesn't really change our result that we end up getting samples on the DTFT. It just makes them more closely spaced. So now the total number of samples is NZ. That's the actual non-zero ones plus the ones that are tacked on. And since NZ samples are going into our DFT, our spacing now is 2 pi over NZ, which is smaller than 2 pi over N because NZ is larger than N. So this is just a trick to make the spacing finer. So here's a little example. Suppose we have a signal that is 1 for 0 out to 2q, and it's 0 otherwise. So it's a little rectangular pulse. And we can write this in terms of our p sub q. Remember, p sub q goes from minus q to q, so we really just have to shift this thing out by q. And this will require us to use the delay property for the DTFT to understand this. So we look at our DTFT table, we find out that the Fourier transform of this thing, the DTFT, is this sink-like thing that we were talking about before, and then we just account for the delay property. So this is the actual DTFT of these signal samples, and if we were to take and collect these ones and take our 2q plus 1 non-zero samples, compute the DFT, we would just be getting values on that actual DTFT. So we can immediately write out what the DFT would be for that case. Now, if we don't zero pad, then all but this first DFT values are 0. So if we don't zero pad at all, you plug in all the k values here, you'll find out that this numerator is 0 for every k value except for k equal to 0. Well, actually it's 0 for that too, but so is the denominator. So L'Hopital's rule evaluates that out to be equal to 1. So that doesn't really show what the DTFT looks like, so we need to use some zero padding. So here's a couple cases using zero padding. So Q is equal to 5. So our total number of non-zero points is 11. And we're going to zero pad 11 zeros onto that so that we have a total number of 22 points. 11 non-zero, 11 zero. And so now the DFT points that we get are these things right here. All those. Now, notice how they fall perfectly on the blue curve, which is the actual DTFT curve computed for over the range minus pi to pi. Notice that I'm using a normalized radians per sample here. I'm taking omega and dividing it by pi. It's just a little trick that I do all the time to allow me to easily look at things on an axis from minus pi to pi. MATLAB doesn't like to put grid points at pi. Now, what would happen if I didn't do the zero padding? I've doubled my length with zero padding. So that means that I've made the spacing half of what it would be without zero padding. So without zero padding, I'd lose every other point. I'd lose that one, that one, that one, that one, that one, all of these. And so now we see that what we stated above is actually true. If you were to take the DFT of just 11 ones, don't do any zero padding, you'd see a number there. You'd see 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So yes, even though this does lie on the DTFT, what we're seeing is that it doesn't really provide us with a very good view of the underlying DTFT. If we zero pad by tacking on 11 zeros at the end, now we're starting to see a little bit more structure. We've got that. But still, if I only had those dots, I'm not really seeing much of the shape of this underlying DTFT. So if I take and zero pad now, tack on 77 zeros onto the back of this 11 ones, now this is what I'm going to be seeing with my DFT. Now you'll also notice that I'm plotting this from minus pi to pi, so I'm taking those upper points and bringing them down to be the lower points. So the DFT, when I compute it, will go here and then it'll go back up like this. I'm taking all those points. Well, it doesn't go back down, so it goes back up and stays up. So I'm taking these and moving them down to here to make all of this. And there's a command in MATLAB called FFT shift, and we'll talk about that in the actual class. But by zero padding more, I'm now, these blue dots and the stem plot is really showing me the shape of this underlying DTFT, and that's what we really want. So the zero padding, the zero padding really lets us compute on as fine a grid as we need to be able to see, and we'll talk more about that. So here's the code that I used for that. A lot of students get hung up on this. I'm just initially sticking 22 zeros into a vector, and then I fill the first 11 of them with ones. That's all I do. Rather than first putting in 11 ones and then tacking on 11 zeros at the end. I just first fill it with zeros and then put the first 11 as ones. Here I fill it with 88 zeros and I fill the first 11 spots with ones. That's all I'm doing. And so here I'm doing the FFT processing. Simple command FFT. And then here's the FFT shift that reorders the points so that I can plot them from minus pi to pi. And then here is a command that gets the right frequency points to plot the DFTs, and we'll talk more about that during class. Okay, so most of the code here is just plotting and labeling. The stuff in the red boxes are the more important stuff. Now, let's just review some of the important points for this finite duration case. The DFT points lie right on the DTFT curve. We only get a good view, though, if they're closely spaced enough. And we saw that zero padding doesn't change the shape of the DFT. It just gives us a finer grid on which we're computing. And so all of that is good stuff. But we now really need to think about the case where there are non-zero samples that we're not collecting. So the infinite duration case is more representative of reality. So the signal, quote unquote, goes on forever, or at least for a long time, longer than we can collect samples. So we only grab n samples somewhere out of the middle of this. We'll just say that we start at 0 and go to n minus 1. So we've lost some information. So the DFT that we compute from these samples does not include the information from the non-zero samples that we haven't collected, obviously. But what we want to compare is the DFT that we can compute to the DTFT that we could compute with all of the samples, because that's really the gold standard, so to speak. So first what we're going to do is relate the real signal, the full duration, infinite duration signal, to the one that we can see. We can only collect n samples. So those two are equal to each other only over this range. But then what we're going to do is imagine that for the purposes of thinking about the summation that we're going to do, if we put zeros everywhere else and we happen to add up contributions of those zero elements, the fact that they're zero means that they're not contributing to the sum at all. So we have this idea of an imagined finite duration signal. We're just imagining zeroing out all the values that we haven't actually collected. So the same information is in x sub n as the actual samples that we've actually collected. That's the important point here. Now we can imagine computing the DFT of these n collected samples. And here we're summing from n equals 0 to n minus 1. So really here there is no distinction between subscript n and no subscript n, but it does help us keep some notational perspective here. So the question is, I've computed some DFT points. Where do those relate to the DFT of the full, complete signal? That's the question that I want to answer. So how does this DFT of the truncated signal relate to the true DFT of the infinite duration x of n? And that's what we want to try to answer. So let's have some notation here. We've got this signal. We can imagine that we have it for all time, minus infinity to plus infinity. We can at least write that down and wish for that. That's the true DTFT. There's no way we have access to that, but we'll use a subscript infinity there to indicate that symbol. But that's the thing that we're trying to see. We're desperately wanting to see that thing. But this is the thing that we're able to see. It's the full summation DTFT, but operating on this truncated signal. Now that's the same as the DFT of just the samples that we have. So this will be called the DTFT of the truncated signal, and we'll use a subscript n to indicate that this one is for the case of having collected n samples starting at 0. And we haven't really seen it yet, but what we will see is that this is a distorted version of the thing that we really want to see. So the DFT of our collected signal data is just found by replacing this omega by the appropriate 2 pi k over n, just like we've been doing in the past, and we'll put a subscript down there to indicate that this is a DFT for n data points. That's what we can compute and see. So the question is, this is what we can see. This is what we'd want to see. How are those two things related? That's the question we want to answer. And more importantly, if they differ, how can we minimize that difference? So it is easy, though, to see that this thing is really just samples of this thing, which is this. So we know that that is true. The DFT of the collected data samples of the DTFT gives samples of the DTFT of the truncated signal, but not samples of the true DTFT, because we're missing some of the terms. So clearly they can't be equal to each other. So what we've just seen is that if we collect some chunk of data from the center of the signal, there's no way that we can see this perfectly. We can only see this thing. So now the question comes down to understand what we can see, we need to see how these two things are related to each other. So we'll now try to figure out how to relate x sub n of omega to x sub infinity of omega. And we will characterize that in a series of errors. What kinds of errors are there? Distortions, discrepancies, and if we can understand those, we'll be able to do a really good job of trying to figure out how to do this properly. So that's what we need to do. So first we can say that we can write this in this simple way. We take our complete signal x of n and we multiply it by this rectangular function that just sets to 0 the values that we haven't actually collected. Now we know that the DTFT of this thing is this sinc-like function. And we have this property. We haven't really explored it too much yet, but we do have a property here that says that if you take the DTFT of the product of two things, that the resulting DTFT is this integral that does what's called convolution of those two different DTFTs. So what we can see is the relationship between this thing, we can compute points on that, and this thing, which we really want to be able to see. The thing we want to see kind of gets all smeared up with this function to give us this one. And if we understand what that smearing does, we have a better idea of how this all works. Now when you go on to a DSP class, you'll learn more details about this smearing idea. So we're only going to touch on it and talk about it in rough terms. But the basic idea is xn of omega is the thing that we can find points on, but unfortunately it's a smeared version of the thing that we really want to see. But here's a fact. The more data that we collect, the more this thing becomes like a delta function, and the less it smears as it goes through this integration process. So let's take a look. Suppose, this is just a lot of supposing, suppose our infinite duration signal has some nice DTFT that looks like this thing. What will happen is once we collect a finite amount of data, the underlying DTFT is now going to be some sort of smeared version of that. So you see all these places where there's sharp edges are now smeared. Now this is kind of a cartoon version of this, but it's pretty accurate to what really happens. There are some things that I'm not capturing here, but it's pretty close. It captures the essence of it. Now, when we take the samples that we've collected and we compute the DFT, we're actually getting points computed on this smeared thing. So here's all of our points. They're showing up on this smeared thing. Now the question is, that does sort of look like this, but not exactly. And so what we need to know is how to control that amount of smearing to enable us to get a better vision of what the true DTFT looks like. So here's some important points. The DTFT of the finite collected data is a smeared version of the infinite duration signal's DTFT. The things that we can actually compute lie on the smeared DTFT, not on the true infinite duration signal's DTFT. So we've got an imperfect view of the thing we really want to see. And if we used zero padding, it doesn't give us a better view of the non-smeared one, it just gives us a better view of the smeared one. But that can be helpful. So for example, if we were to go back to this example, if we were to collect, or if we were to use zero padding, and say zero pad out to double the length, we'd get more points here. And now we'd be able to see a little bit better perhaps what this thing really looks like. But it doesn't undo any of the smearing. The smearing is still there. So zero padding does not fix that smearing issue. So here's all the connections between what we have. We've got some signal that might have a CTFT that looks like that. I'm indicating where our fs over 2 is. We can see that there is some significant stuff outside of that range that's going to contribute to aliasing. After we sample, we've got some amount of aliasing. We can see that this doesn't swoop down like our true CTFT does. So there's an error due to sampling. Then we collect a finite amount of samples, and that causes some smearing. So these nice sharp peaks now are smeared out into duller peaks. And then finally we compute the DFT, and if we don't do any zero padding, we're only going to see a coarse grid of points there. If we do zero padding, we'll be able to see a finer grid of points there. But again, it doesn't get rid of the smearing. So here's a summary of the errors that we're seeing in this kind of processing. Going through the A to D converter, we see that there's aliasing error, and we can control that through proper choice of the sampling rate as well as with anti-aliasing filters. There is the smearing error from collecting a finite number of data points. We can control that by trying to collect more data, and we can also control that through the choice of a so-called window function that we apply after collecting the samples. And in this lecture we're not going to talk any more about that. Then there is finally the grid error, the fact that when we finally do get around to computing the DFT, we're only going to see a certain number of points on this smeared thing. But we can control that partly through choice of how many samples we collect, but we can also control it through zero padding. So notice that increasing the number of samples that we collect helps us in two ways. It reduces this so-called grid error, and it also reduces the so-called smearing error. So this is the only thing that we can compute, and if we have attended to all of these errors, hopefully by looking at that DFT we can get a good idea of what the CTFT sort of looks like. And if we haven't addressed all these errors, we can make some mistakes, and that can be costly. So just again want to point out that this zero padding trick that we would use here just simply allows us to calculate on a finer grid more points on the smeared DTFT. That's all. So we'll go through a lot more of this during the class and look at some examples of how the processing works.